Hello and welcome to Thinking Clips. Today we're going to look at measuring time. Now this gentleman here, Galileo, or Galileo if you're a Queen fan, realised that in order to understand motion, there needed to be an accurate way of measuring time. And one of the ways he did this was to look at pendulums. Now he noticed this apparently when he visited cathedrals like the Sistine Chapel, and noticed that the periodic motion of these chandeliers swaying from the ceiling gave a constant time period. Now, how did he do this without an accurate measuring device himself, like a stop clock as we would use today? Well, apparently he used his own pulse as a very rudimentary type of accurate timing device. And the things that he worked out about motion, which we're going to see a lot more of as we work through the subject of physics, are the laws of motion that we still use today, and even putting astronauts in space and satellites and so forth still use the ideas of Galileo. There's a practical activity to realize just how inaccurate time measurements can be. I would advise that you take a stop clock. It could be an old-fashioned one like this, could be a more modern one like this, or the sort of thing you get on a smartphone, and just measure a very simple but quick event, such as an object falling from a fixed height, down to the floor, over and over again, and write down your measurement. Now, you're probably going to use a modern stop clock, and a lot of them can record the time to even 1/100th of a second. So that is 0.01 of a second. Now the second is what we call the base unit of time when we use it in physics. So the second, with this symbol S here, is what we call a base unit. What this means is that other units, like meters per second for speed and velocity, are based partly on a base unit. The other one is obviously the meter, which we'll look at next lesson. So you might think that these devices are very accurate, but if you keep repeating the same measurement and observation, what do you notice? Now, I think you'll notice that each time you'll get a different reading on your stop clock. Even though the ball could be dropped from exactly the same height and it falls at exactly the same rate in the Earth's gravitational field, you're likely to get a different reading each time. Okay, the number of whole seconds might be the same, but definitely the 100th of a second and even this 10th of a second here will be slightly different each time. So we could ask ourselves, is the stop clock we're using a precision instrument? Well, the answer is yes. It gives us a high resolution. 100th of a second is a very short period of time. And so it is a high precision instrument in many regards. But is it an accurate way to measure time? Well, the answer to that is, of course, no, because if you're getting different reading each time, and particularly they're not very close to each other, then we would say we have a low accuracy. So we define accuracy as how close we would be to the true reading, to the actual true result. And the real problem in this is, of course, that the person controlling the stopwatch has what we call reaction time. Just as people have different reaction times in sport and safety conscious events like driving a car and having to react and put your foot on the brakes. We are aware in everyday life that people have a reaction time. So when you are using a stop clock, your reaction time is generally about 0.1 second, a tenth of a second. So this means that you are likely to be out of the true reading by about 0.1 second each time. And that's plus or minus. Sometimes you can be too quick, sometimes you could be too slow. So that limits the accuracy of a digital stop clock that can read to 100th of a second or even a millisecond, which is a thousandth of a second, even though it's a precision instrument. When it's used in this way, then it lowers its accuracy. Okay, so what about pendulums? How would you measure more accurately the time period for a pendulum? So let's just think about what we mean by the time period, first of all. So as Galileo was looking at the chandeliers attached to the ceiling of a cathedral, then what he was trying to identify was how long does it take the chandelier, which is a very rough pendulum, to move from its furthest extension here all the way to the other side at its furthest extension and then back again. So that is what we call one period of the swing or oscillation. So how would you go about timing one period or the period of a pendulum swing? Well, hopefully you realize by now, if you just try to do one swing at a time, the answer would be quite inaccurate, because using your stopwatch, you would find that you got a different answer every time because of your reaction time is plus or minus 0.1 of a second too fast or too slow. So when you're trying to measure short events of time, short periods of time, then you should measure multiple periods. So, for example, 10 swings or even 20 swings. So you're measuring 10 or 20 time periods. And then if you think about it, that is 10 times as long as one swing will be. And so the percentage inaccuracy of your 0.1 second plus or minus is going to be much less. So that is what you need to remember if you're asked how to measure a short time period accurately for repeated events. Measure many, add them all together, and then divide by the number there are. And then you get to the average. Here's also a good reminder of how we should set out our results in a results table. So pencil and ruler, or these days you might do one on a spreadsheet. But make sure you put accurate, informative headings in the columns. So the time for 10 swings and the units you're using, in this case seconds, and then the average time for one swing. Now, if you've got time after you've built your pendulum, you only need some string, something to support it from, and a small weight, a piece of plasticine will work. You could investigate how varying the length of the pendulum affects the period, but today's lesson is more about the time than the length. So is there a more accurate way to measure time in physics? Well, with technology, of course there is. So these are light gates, and these remove human reaction time completely because the timing on and off is not controlled by a human at all. So this is an air track with some trolleys on the air track. The air track is just a low, very low friction surface, a bit like air hockey. And these trolleys can move along the track, but they have these pieces of card sticking out the top. And as they pass through a light gate, then they will turn on or off the timing device. And so there is no longer this 0.1 human reaction time, 0.1 second human reaction time. So that is another way to measure time accurately if you can't do a repeated event like many swings of a pendulum. So let's just finish off with a typical exam question about time, which I'd like to thank Cambridge examination board for. Okay, so this is an old Cambridge question. Let's have a look at what was asked in this one. So it says the clock on a public building has a bell that strikes each hour so that people who cannot see the clock can know what hour of the day it is. At precisely 6 o'clock, the clock starts to strike. It strikes 6 times. At the first strike of the bell, a man's wristwatch is shown. When the bell strikes for the 6th time, the wristwatch is shown as in figure 1.2. So we can see the difference between the positions of the second hand here and here. And the first part of the question, A, says calculate the time interval between the first strike and the 6th strike. So pause the video and have a go at that yourself. Okay, so hopefully you worked out that on an analog clock, and you do need to still remember how analog clocks work, if the second hand is on the 1, these divisions here are 5 seconds each. So this will be 5 seconds. And then here we have 5, 10, and so here we have 15 seconds. So the man's wristwatch has gone from the second hand being on the 5 second to the 15 second part of the clock face. So we can say the time interval is 15 seconds, subtract 5 seconds, which is going to be 10 seconds. Okay, we'll just move on to the last part of the question. Calculate the time interval between one strike and the next. Okay, let's go back and think, well, how many strikes were there? It said it strikes 6 times. So over this 10 seconds, there were 6 strikes. But we want to know the time interval. So between 6 strikes, there must be 5 intervals. If you think the strike is dong, 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 between each of those dongs, we had 5 intervals. So what we can say is we need to divide the 10-second time interval between the 5 intervals. And so our answer will be 2 seconds. The last part of the question, C, says at precisely 11 o'clock, the clock starts to strike. Calculate the time interval between the first strike and the 11th strike. So we're assuming the clock works at the same rate. So using the same analogy before, I won't do 11 dongs. There'll be 10 time intervals between the first strike and the 11th strike. Okay, so this time we have 10 time intervals. How many? So I'm going to write here time intervals so we know what we're talking about, and we're going to multiply by the time for each time interval, which we worked out above here was 2 seconds each. So our answer will be 20 seconds. So some very simple answers there, but hopefully you understand how you use the analog clock to work out different time intervals and periods of time. Okay, we're going to finish there, and I hope to see you again next time. We'll be looking at the base quantity of length.